Hello. So we're moving on to chapter 15. This is electrophilic aromatic substitution. So now in chapter 14 we talked about benzene, and now we're talking about some of the interesting chemistries with this. The first one is actually adding groups onto benzene, and they're all going to work the exact same way, the same general way, the same three steps. Okay. So what we're going to be doing is we're going to be so you have a polar covalent, sort of an electrophile and sort of base. So here, what we're going to be doing is we're going to be swapping a hydrogen for this electrophilic part of a bond. Okay, and we're going to be doing a whole bunch of different things, putting halogens on there, nitrating, sulfonation, Friedel-Crafts, alkylation, and acylation, so making new carbon-carbon bonds. We're talking about all of these, but they all use the same general mechanism. Okay, so if you remember back from the alkene, right? So we had the double bond coming in and attacking, and then pushing the bromine away. Through the carbocation, this came back, and the negatively charged nucleophile is going to come back and attack the carbocation here, and you get addition product. Okay? What's going to happen here is you're actually going to get substitution. Okay, and so what's going to happen is you have you need to make something that's positively charged. Okay, polar covalent bond. We'll talk about how to do that in a minute. You're going to get the double bond, again, going to be attacking here, pushing that away, right, to get the carbocation. Now, again, you're going to be, now the nice thing with benzene, right, is you can do resonance structures around the ring to help stabilize that charge. Okay? And then the negatively charged thing, instead of coming in and attacking here, right, we're going to be removing the hydrogen where the electrophile was, where we added it. Right? Because remember, you can only have one group per carbon in a benzene, right? Here you'd have two, right? So with that, but the nice thing is, right, we're going to reestablish the benzene that the electrons in the two electrons in the CH bond are going to be this new carbon-carbon double bond here, okay? So with that, and so the first step is always really slow, right? Because what you're doing is you're breaking up the aromaticity, right? So it becomes aromatic to non-aromatic, right? Because we have basically an sp2 hybrid carbon. When we remove the hydrogen, what we're doing is we're reestablishing the benzene, and so that's the molecule goes, and it's a lot easier to get to. So the overall mechanism is we're going to have benzene. It's going to attack a positively charged thing. That negatively charged thing is then going to come back and grab the hydrogen. Okay? So to do this, almost invariably we're going to need some sort of catalyst, okay? And so usually what we focus on is chlorine, bromine. Fluorine and iodine, they're going to do this. They're going to need slightly different ways of doing it, but it's essentially the same mechanism. Iodine, you need, again, you're going to need I plus, F plus, but F-tia, and I2 copper chloride. Okay? So for that, but we'll focus on the mechanism for this one first, okay? So what ends up happening is, so let's say you have your benzene, okay, and you have bromine. Okay. So the way that I usually like to visualize this, Fe3, okay, and so bromine, okay, I'll have that, I'm going to put the hydrogens here, just so you can see them. Okay, step number one, this is a Lewis acid. It's searching for electron density. And so this is going to attack here, and what it does is it actually busts this, it actually takes these two electrons with it. Okay, so what you end up with is Br plus with only three, because it only has three sets of lone pairs, so the plus charge, and FeBr4 minus. Okay, so this is always step one. Okay? You have to generate the positively charged thing. Next step, you're going to get, this is going to attack the positive charge. Okay? So this is going to be step two. Now, the nice thing. Okay? So we're going to put the bromine there, hydrogen there. All right, we didn't do anything with those other two, these other two double bonds, so they're still there. But this carbon only has 3 bonds. Okay? So and the nice thing is, right, we can do resonance structures to go around. Okay. So now this has a positive charge. And if we can do another resonance structure where we remove this, there. Now, that's all fine and good, but what we really want to be able to do is take this, rip off this hydrogen, and reestablish the benzene, and this is step 3. So when that happens, right? Bromine plus HFeBr4, which is really just HBr plus your catalyst. That's how all of these are going to work. Okay. Yeah. Step 1, generate the positively charged thing. Step 2, the benzene attacks it. Okay. And you get the resonance structures as part of step 2. Step 3 is going to be whatever that negatively charged thing is going to come back and extract that hydrogen from where you added your group. That's it. That's all we are. So nitration, right? So you have nitric acid plus sulfuric acid. You heat it up, you need both acids. But again, what you're generating is NO2 plus. Okay, you just you lose a water. This is catalytic acid. You lose a water to make it. And then the next steps are exactly the same. So again, you're going to make the NO2 plus, which gets attacked by the benzene. That's it. SO3, again, we're going to be generating this SO3H plus, okay, which gets attacked by the benzene. Okay, same steps. Now, Friedel-Crafts, exact same mechanism, okay, but we're doing it we're going to be doing making carbon-carbon bonds, okay. Now, for this one, because we're having to break a carbon-chlorine bond, we have to use a little more powerful Lewis acid. So here you're going to need aluminum chloride. Okay, but the mechanism is still the same. Okay, it's still going to be this coming in. Okay, so alkylation. Okay. So Cl, pairs. AlCl3, right? So again, just like the chlorine, right? This is going to attack there and suck those electrons with it. And so what you're going to end up with is this positive charge and AlCl4. Right? Step 1. Step 2, benzene attacks, right there. Right? And you can get the resonance structures. Right? Do the resonance structures. Okay. Step 3, right? So this is step 2. Step 3 is this attacking, this grabbing, acting like a base, grabbing that hydrogen, and those collapse down. So number 3. No problems, right? It's the same mechanism we had with the other side, okay? And then you regenerate your catalytic plus HCl plus AlCl3. So if we were doing this, right? So that's we're doing AL. This would probably be AlBr3, but that's okay. So we're doing this one. AlBr3. So this is going to attack there. Take this along. It's going to have that, which this comes in, grabs. This. And then step 3, right? To make AlBr4. This is going to attack here. That hydrogen, which is going to collapse down, and regenerate your benzene. Like that, or however you want to do So where this, where the bromine is here, that's where it's going to attach to the benzene. Most of the time. So you're going to end up with this. Now, the problem is, with the alkylation, is the formation of this carbocation here. Okay? Because if you do this reaction where you have the aluminum at the ends, what you're actually going to get is the isopropyl benzene and not this. And the reason for this is the fact that you're forming the carbocation intermediate, and after this first step, this is unstable because it's a primary carbocation. You'll get a hydride shift to move it to a secondary carbocation, then the benzene will attack. This is what it will see. And so you end up with the isopropyl benzene, as opposed to just regular propyl benzene. Okay. The other thing is, for this, the bromine or the chlorine has to be on an sp3 hydroxide carbon. It can't be hanging off of a double bond. Okay? And so it can be next to a double bond, no problem. But it can't be directly on a double bond. Okay? So if it's on here, it's not going to work. And the benzene, not going to work. But here, it's a regular sp3, right? Even though it's next to a benzene, no problem. So, okay. The other thing is, this is, oops, I don't know why that's, oh wait, yeah I do. This is actually a way of generating isopropyl. This is actually slightly activating. We'll talk about that in a minute. And so this is slightly more reactive than this, and so this is actually, if you have enough of this around, you're going to get a significant portion of this as well. Or adding a second dose. It's tough to have it just stop at one. The alternative for this is what's called acylation. Okay? And so, again, it's going to be the same mechanism. Okay? But you don't have to worry about the rearrangement. Okay? And so the reason for that is, so let's say you're doing this, there's all pairs around here. So you have the AlCl3, okay? Again, same first step, there. What you're going to end up with is this plus the AlCl4. Now, the nice thing is for this is there's actually a really nice resonance structure where these lone pairs can come down here. Oop, let's turn this up here. So you can get this resonance structure to stabilize it, so you don't get the rearrangement. And so then this is going to come in and attack. So you're going to end up with hydrogen, right? And so step 3, this is going to come in and grab this, collapse down, and so you're going to end up with that. But notice how you're not going to get the rearrangement. Okay? And it all has to do with the fact that these little pairs are right next to the carbocation, so you're going to get the stability there. Okay? Because of this resonance structure, don't have to worry about the stability. So if you do this reaction right, you're going to get rearrangement. Right? Because you make a primary carbocation, you're going to get the hydride shift to go here, it's going to go there. But if you do it with the acylation, you can get these carbons as you need it. 1, 2, 3, 4. You're not going to get the rearrangement. It's going to go directly from here into where that the chlorine is hanging out. Okay. One of the limitations for this is that you can't have these deactivating groups. Okay, they actually suck electron density out because they put a positive charge right next to the ring, and so pulling it out. And so if you think about this, it's you're taking gunpowder out of a bullet, and so therefore it's it's not going to have as much oomph, right? So you can't do this. So if you have a deactivating group, so C double bond O, N double bond O, S double bond O, you'll have a S double bond O, you have a halide, CF3. This reaction just is not going to work. This is already slow enough, and you put a deactivating group on there. The carbon-carbon group is just not going to be able to get added. Okay? The other thing is you have to be really careful if you have amines on the around aluminum chloride, because what will happen is you'll get these lone pairs will actually come in, and the lone pairs and the amine will come in and attack the aluminum chloride, and then you'll complex your lewis acid, no more catalyst, no more reactions. You have to be careful. You have to mask this if you want to have it on. Okay, so excuse me. So this is great, right? So that because you don't have to do the alkylation, right? But the problem is, how the heck do you get rid of this, right? If we want to make the propylbenzene, okay, we need to get rid of that. Okay? So the way that we do this, there's actually a couple of different ways we do this. Clemenson and Wolff-Kishner are very similar to this, and actually they'll work on it. They're sort of general reactions, okay? So about that, and so what they do is they turn C double bond O's into CH2s. Okay, Clemenson is under acidic conditions. This is zinc, the zinc mercury amalgam under acidic conditions. The other one is Wolff-Kishner, which is a hydrazine under basic conditions. But they both end up working out the same way. Right? The other way that you can do it is a hydrogenation. Now this is a very special case where the CH2 has to be directly adjacent to the benzene. If it doesn't, not going to work. You're just going to end up getting this. Stuff like that. And so there's different ways of doing this, okay, the same reaction, because as the molecule gets more complex, if you don't, let's say if you have groups that are sensitive to acid, you're going to want to do the Wolff-Kishner. If you have groups that are sensitive to base, you can do the Clemenson. If if you have a hydrogenation that works, no problem. Stuff like that. And so you have flexibility in doing the exact same thing. Okay? And so if you want to make the butylbenzene here, you can't go directly to it because you're going to end up here. You're going to have to go sort of the back route and sort of put it on as an acyl group and then get rid of the C double bond O through, say, hydrogenation. Stuff like that, to get it there. You can't go directly. You have to sidestep. Something like that. So, okay, so electron withdrawing groups. Okay, they're going to generally slow down the reaction because you're pulling an electron density. Electron donating groups are going to speed it up. Okay, so how do we figure out what it is? Okay, it turns out you can look at this list. So things that are electronegative, so halides, okay, they are deactivating because electronegativity is going to suck things away. Again, if you have these at C double bond O's, C triple bond N, this is an S double bond O, this is an N double bond O, a positive charge next to it, those are all going to be electron withdrawing, right? Because the electrons within the ring are going to be attracted to either that positive charge of those groups. Electron donating groups, okay, are things that put either alkyl groups, okay, so just regular sort of methyl, ethyl, propyl, isopropyl, whatever, or things that have lone pairs directly next to the ring. Like that. So it turns out that when you have these, okay, if you have lone pairs or an alkyl group right next to the ring, when you add the next group on, it's actually going to be ortho. It's going to go into the ortho pair direction. If you have one of these groups with S double bond O's, N double bond O's, C double bond O, C triple bond N, some of that, those are actually going to put the next group into the meta position. Okay? And so. Yeah, and so if we look at this for predict the product, right? So it doesn't matter what the group is that you're putting on. It's who's already on the benzene that's doing the directing. Okay, so if we have toluene here, so HNO3, H2SO4, right? So this is going to put a nitro group on here, but this one is orthopara because it's an alkyl group, so it's going to want to put it here, here, or here. So you're going to get a mixture of a little bit of nitro here, right? So the ortho or the para. Okay. Again, with this here, you're saying, hey, but that's a meta director. Nope, doesn't matter. This is what's already there is directing where the next one is. Okay, so in H2. The lone pairs next to the ring. You do this nitration. Right. Again, it's going to be orthopara. So you're going to get a mixture of the ortho product and the para product. Okay. We have benzaldehydes like this. Remember, we have a acetyl bond O next to the ring, so that's going to be a meta. So that's 2 away, so it's here and here. HNO3, H2SO4. NO2. So the groups that are on there are going to make a difference. Okay. Now, why is that? Okay. Now, here I'm just going to go ahead and draw it out. Here, you can look at the slides, stuff like that, but it all has to do with stability, shockingly. So let's say we had phenol. Okay. And then let's say we're going to do the add chlorine to it. Now this works for all of them. Okay. So like that. So FeCl3. Okay. First step, right? It's going to be here. Pull that away. And so you're going to end up with the Cl plus and FeCl4 minus. Okay. Now the benzene is going to attack. Okay. Now it has 2 options. Okay. You can either, all right, so we're going to use this double bond. Okay. It can either put the chlorine here, okay, with the positive charge there. Or it can put it with the chlorine here. The positive charge there. Okay? Now, let's look at the resonance structures. Okay, so right, this one here and this one here can't participate, but we can, right? So if it's looking for help, right, it can't look this way, but it can look for this carbon, and this carbon can shift things over. So you get this. Right. Again, we can shift this over. Here. Right. So COH. But we stop there, right? Because this one can't help. So not too bad, right? So like that. So for here, right, again, we can shift that over. We can make this. Again, we can do this here. Okay. Now, because we're doing it here, we can have an extra resonance structure where this lone pair is right next to it. Because the lone pair is right next to the chlorocation, we can get this. This is the key. Because we can't access this resonance structure if we put it in the meta position. Okay, we can only do that if we can put it in the ortho, or it would also work with the para. Okay? Stuff like that, and so it's going to want to go, instead of this way, it's going to want to go this pathway because it's better able to stabilize that carbocation. Okay. Now, so with that, so let's say, so that's why having lone pairs next to it are going to put things ortho-para. Okay, so chlorine doesn't make nitrogen, nitrogen, whatever. It's going to have that. So sulfur. Okay. With the alkyl group, it's the same thing. Because that's, you go through the same treaties, and so let's say you do this with toluene, you would end up with this intermediate here. Okay. And notice how this is a tertiary carbocation. That's going to allow you to, at least at some point, have a tertiary carbocation, which is going to be more stable, right, than all the other places that are going to be secondary. Stuff like that. And so that's why alkyl groups end up being ortho-para. It's not great. I mean, it's not a huge incentive, but it's something. stuff like that. And so so that's why they're also ortho directly. Now for the meta, similar reason. It's similar reason, but somewhat. Okay, so let's do that same reaction. Okay, but a nitro group, if you draw it out, is going to look like this. Okay, it actually has a nitrogen with a positive charge. Okay, and so like that, it's actually zwitterionic. Okay? So like that, and so again, we're going to do this, right? So chlorine. Oh, I should have kept this going. Sorry for this one, right? So this one is going to eventually grab this, collapse down, so you end up with. Sorry, should have finished this off. So in this case, you would have gotten that. Okay. Again, we're going to do FeCl3. So first step, same as always. We're going to make Cl plus FeCl4 minus. Okay. Again, this is going to attack, and it's got a choice. Okay. So we can either do B and go into B. Ortho position here. Or it can go into the meta position, right, if we were using that double bond. Oh, this should be CL. Sorry. Again, we're going to do resonance structures, right? So here, right, there, CL, not too bad. Okay, we do another resonance structure, which puts the positive charge there, and so hydrogen. The problem with this resonance structure is, remember the structure of the nitro group. Here, the problem is this. Okay, you're trying to put two positive charges right next to each other. That is really, really bad. Okay? So like that, and so that's why it goes into the meta position. Okay, because it's not going to work. By putting it in the meta position, right, we can avoid this. So you end up with positive charge there. Again, you're going to be able to at no point. Right, so you're going with this case, right, you're going to have a positive charge here, positive charge here, positive charge here. You're not going to be able to have that situation where there's two positive charges right next to each other, and so it's going to go into the meta. So in the ortho-para case, it's taking advantage of some extra stability here. Okay? In the meta case, where you have electric withdrawing, right, what it's doing is it's trying to avoid a bad situation. Okay, it's trying to make the best of a not so great situation, and so you're going to see this, right? It's going to grab that hydrogen, collapse down, so you're going to end up with the meta. And that's why all of these are the same way. It's all about stability of the resonance structures. Okay. And so that's what these fancy things are. So like that. And so that's just what we were doing here. Now, this is a nice little chart. So again, ortho-para directors are things that have lone pairs right next to the ring, okay? Or alkyl groups. These are deactivating, right? But they have lone pairs next to the ring, so they're ortho-para. Meta directors, C triple bond N, S double bond O, C double bond O, N double bond O. It's like that. Okay. Now for tri-substituted benzene, so like that. So if you're trying to make that, you already have two groups on there. Okay. Now the question is, what do each one of those do? So sometimes you can get it reinforced, right? So this alkyl group, right? It's gonna want to go ortho, right? Or para. The para has a nitro group. This NO2 is a nitro group, right? It's a meta director. Okay, so meta to that is 2 away, so it'd be here. So they're both directing the next group. So in this case, bromine to go here, right? So it's no problem. If instead you have this, right? This is an ortho pair director, so here, here, and here. The meta director is here. Now they're not. Okay, now they're conflicting. And so the question becomes, who wins? Okay, pretty much everything's going to be in an alpha. Okay, and so so it doesn't matter if this was a butane. Okay, it's not going to be as powerful of a directing group as the OH is, and so it's going to follow the OH's lead and put the next group here in its ortho position. Okay, now. Even if you have reinforcing, okay, if you have 1,3 substitutions like this, like that, the problem is you can't, even though it wants to go here, okay, they will both reinforce to go here, there's just too much steric bulk to do that. You can get it here, you can put it here, you can put it here, they're both reinforcing for that. They would both be reinforcing for this, but there's too much steric bulk, so you're not going to see this. So it actually just needs these two. Okay, so carboxylic acid looks like this. I would draw it up. I want to get you guys used to seeing it CO2H. Okay, so we're going to add chlorine. You can see CO3. Right? So this one, right? This is an alkyl group, so it's ortho. So it's ortho. This one here is a C double bond O, so that's a meta director, so it's going to go here and here. Right, so they're both reinforcing to the CH3, so chlorine here. So that's what you need. Now for this one, so remember you got lone pairs here. So chlorine FeCl3. So again, this is orthopara. So orthopara. Now for this one, right, this is also orthopara. Right? So we can go here, we can go here, right? But we can't go there because it's too much steric bulk. So OCH3. So you're going to put the chlorine there, F there. CH3. Right, circle for just the benzene. Right, so you get that one, but you're not going to get the chlorine there. Okay. So for this one, right, so this one is going to direct it ortho, para. This one here is going to direct it meta, which would be here, here. This is going to be more powerful than the alkyl group, so it's going here. You can't go there. It's no way to substitute there. It's at that place is already substituted. So there you go. Now, as some side reactions, okay, that occur in this, so it turns out that if you use a compound called N-bromosuccinimide, which the structure is right here, you can swap out a CH bond for a CBr bond next to a double bond, right? So here's a carbon-carbon double bond right next door. There's a CH bond here, right? So NBS we can swap it out. Here, right, It's next to a double bond. There's a CH next to a double bond, so we can swap out one of the bromines. Now, you have to be careful. You have to be careful, okay, because you have to make sure that there's a CH bond. Right? So for this one, CH3, CH2, right, CH2, CH3. Right? But this is just a C. So if we dump in a bunch of this, right, we can add it here. We can add it here, but we can't add it there. Yes, there are CH3s here, but they have to be right adjacent to the ring. Okay? And so, and you really only get one bromine per site. So you're going to get CH2Br, this, and then here. Alright, so you're going to end up with that. So, kick it old school right, from the last test. Right? So, right, if we had HBr, H2O2, right? So we're adding to the double bond here. This is secondary. This is primary. We're doing with peroxide, so it switches the priority. So you end up with bromine here, a hydrogen going there. Like that. For this one, so F3C, and DS. Right. Here, right, so here we have right, two hydrogens. Right. Here we don't have any, so we can't go on this side. So right next to the double bond, right, so it ends up being, we swap out one of those hydrogens for a Br. Now, the other thing that you can do is if there is any sort of alkyl chain, if you hit it with KMNO4, it'll actually lop off that chain and leave behind a carboxylic acid. Doesn't matter how, as long as it's not quaternary. Okay, so again, you need a CH bond. You can lop off the rest of that chain and leave the scar you leave behind as a carboxylic acid. This is incredibly important for the production of polyethylene terephthalic ester, or PET. So this right here, so you have the paraxylene. Right? So with that, if you oxidize both sides of this, now industrially they just use oxygen and some catalysts, whatever it is. But if you mix it with ethylene glycol, which is so that was a fairly common chemical, you can make this. And so this is really good for making plastic water bottles, waterproof fabrics. That's why you want to recycle your if you get a plastic water bottle, you want to recycle it because it's really easy to turn it into fabrics. And so it's easily recyclable. So if you want to reduce this down, if you want to take the the benzene down to a cyclohexene, okay, you're going to have to force it, okay, because what you're doing is you're breaking up the aromaticity, okay, which is not good. So like that. And so if you just do it under regular conditions, right, you just reduce down a regular alkene. In order to be able to do this, you'd have to run it at very high pressure, so like 100 atmospheres. Then you will also reduce the benzene as well. So, but remember, if you have the C double bond O down here in the normal conditions, it will actually turn it into a CH2. Okay. You can also actually, it turns out, do a Birch reduction, which, remember, we saw this before when turning a triple bond into a trans double bond. That's a Birch reduction. So sodium or lithium and ammonia solvent, that'll actually do it too. Okay, so synthesis for this. Okay, so how do we put this together? So not only do we have to think about, the chemistry, how do we put the groups on, but the order in which we put them in there because of this ortho-para issue. Okay, and so typically what you want to do is you want to say, okay, let's work this backwards. Okay, and so so let me draw this out. HCl. Okay, so to get to here, right, we're either going to have to go through this intermediate. We either had to put, last step, you're either going to put this on, or that on, right? Or, so this or this? Oops. Sorry. Right? Put that on there. So just looking at orthopara directing, okay, so this is meta-directing, right, which would be here, here. Right? This is orthopara, which is here and here. Well, here and here, and then there. We need the chlorine to go there. So we can't go through this intermediate. Now for this one, there's two things. One, we have two deactivating groups, and being able to put on a alkyl group onto deactivated benzene is going to be impossible. But even beyond that, right? So this is orthopara directing, right? This is meta directing, right? So it's going to want to go here and here. Where do we want to add the this? We want to add it there. That's not good. Okay, so we can't go through that. But for this one here, right, as far as directing group, right, so this is orthopara. This one is also orthopara, right? We need to add it here, right? So we're going to have to go through this intermediate. So we know that the last step is going to be here, putting this on, which is SO3H2SO4. We know that has to be the last step. So now the question becomes, how do we generate that? Okay, so we have two options. Well, two options, right? So we can either do, put this chlorine over here, or we can go through that, right? Well, this is, right? Well, you're going to have issues with this deactivating, right? But even if you didn't, right? This is ortho and para, right? We need the alkyl group to go here. For this one, right? This is also orthopara, so here, here, and here. We would need the chlorine to go there. So what do? When they're both wrong, when neither one will work, what we need to do is we need to convert one into, these are both into the other, right? So into orthopara into meta, or meta into orthopara, right? So with that, and so we don't have any chlorine groups that are meta, but we do have a carbon group that it is. And so if instead we go through this intermediate, okay, now that's meta, right? So that'll put it here. And so we can go through this to get the chlorine on. All we have to do is get rid of this, and what's an easy way of doing that? Well, we can just hydrogenate it. Right, which is just that. Okay. So here's the question: how the heck do we make that? Well, that's just the Friedel-Crafts acylation. And so you can take benzene plus that, 1, 2, 3, 1, 2, 3, and in the presence of aluminum chloride. Okay, so we have to go through this intermediate, but really we need to be able to get it to here so that we can put the sulfonic acid on. Okay. So with that, so this is CO2, CO3. I'll go that. So you put the acyl group on here. That puts your meta director on, so you can put on the chlorine. Right? Then you got to get rid of this to go to here, and then you can put this sulfonic acid in. Right there. So there you go. There's your synthetic strategy. Okay, this is incredibly important, right? Because there's benzenes in a lot of different compounds, right? So with that, animals, birds, whatever, if they're worried about a predator, they can run, right? So with that, or fly. So with that, plants, on the other hand, how do they say don't eat me? Well, they can't run, so they have to make chemical warfare agents, and therefore they do some really interesting chemistry. So like this one, resveratrol. This can be used to make these other natural products. Okay? Doing some chemistry. And then other sort of things, this compound here can actually be used to make an anti-cancer. This compound here has an anti-cancer activity. And so we can use this as a scaffold to make new drugs. So Lipitor, which is one of the classic statins used for lowering cholesterol, so lowering the LDL. So that was based off of a natural product, right? So and actually the chain that hangs off of that is the same chain that's on the natural product. It's just they made it a better drug, right? So with that, and so make it more druggable. So that's the term. So much better properties, things like that, than the original natural product. But they were able to use that scaffolding to know what to look for. Okay, well, good luck.